Good evening, everybody. Please stand for the academic procession as they will enter the hall now. Please be seated.
Good evening, everyone. My name is Louise Warnig, and in my capacity as Dean of the Faculty of Science, it is my great pleasure and honor to welcome all of you here tonight to the inaugural lecture of Professor Wesaal. So, of course, this evening's inaugural lecture is an opportunity for our faculty to celebrate a very special milestone in Professor Kahn's academic career, and we are really honored that you are joining us this evening. Some of you are here in person, and some of you are online. We are especially grateful to all our Muslim family members, friends, and colleagues for attending this evening as you are celebrating Eid today. I would like to extend a special word of welcome to Professor Sibusiso Moyo, our Deputy Vice-Chancellor, Research, Innovation and Postgraduate Studies, who is representing the senior management of the university this evening. Our Vice Deans, Professor Ingrid Revitsky, Vice Dean Learning and Teaching, and Professor Frikkie Scholes, Vice Dean Research and Postgraduate Students, and the Head of the Department of Microbiology, Professor Alf Botha. A warm welcome specifically to family and friends of Professor Kahn. Her mother, Cecile Miller, is here tonight. Her brother, Walid Kahn, and her twin sister, Seham Kahn, who is also DVC academic at the University of Johannesburg. So academia runs in the blood of this family. Wesaal is very thankful for your unwavering support and encouragement throughout her studies and her career, and she also acknowledges the important roles that the late father, Mustafa Kahn, and the late grandmother, Indrina Robenheimer, has played in this regard. I would also like to welcome colleagues from Stellenbosch University and other institutions, and also current and former students of Professor Kahn. And I would like to mention one name, and that is Dr. Ndlovu, who flew in from Botswana this morning. So warm welcome to all of you. It is now my honor to introduce Professor Wesaal Kahn. So, Wesaal obtained the BSc and BSc Honours from the University of the Western Cape, although she did not originally plan to become a scientist. So she applied for psychology at UCT, for social work at Stellenbosch University, and she, according to her, for some obscure reason, for a Bachelor of Science at UWC. So after considering travel time and fees, both Wesaal and her sister decided to enroll for Bachelor of Science at UWC. And in hindsight, I think you will all agree this was the best decision for the Kahn sisters. Wesaal continued with her postgraduate studies at Stellenbosch University, where she obtained both a master's and PhD in microbiology. During her PhD studies, she was based in Düsseldorf, Germany for 2 years. And in 2003, she was appointed as a researcher and senior lecturer at the Cape Peninsula University of Technology. She was leading the biotechnology program at this institution and was later promoted to an associate professor. During her time at CPUT, she was also affiliated with North Carolina Agricultural and Technical University in the US. Wesaal was appointed as a senior lecturer in the Department of Microbiology at Stellenbosch University in 2011 and promoted to an associate professor in 2017. She's currently leading the Water Resources Research Group in the Department of Microbiology, and her research is well aligned with the Sustainable Development Goals, specifically goals number 3 and 6. as she implements cost-effective water treatment systems to ensure sustainable and safe water resources for communities from a low socioeconomic status. Due to the interdisciplinary nature of her research, her impressive network of collaborators includes experts from both South Africa, Africa, and internationally, with expertise in fields such as bioengineering, health sciences, polymer science, risk assessment, and community engagement. What is also noteworthy is that although her collaborators include world-renowned experts, Wesaal acted as senior or corresponding author on most of her recent publications, confirming her role as a thought leader in these research projects. Wesaal describes herself as a microbiologist by profession, but primarily she sees herself as a teacher. So therefore, it's no surprise that numerous postgraduate students have been successfully supervised and mentored by Wesaal. And she's also a very popular lecturer for undergraduate students, as illustrated by the high student evaluation scores she receives. Currently, Wesaal is also serving as the chair of the Faculty Social Impact Committee. Wesaal, we are looking forward to hear more about your water research, focusing on innovation in water quality monitoring for accurate risk assessment and multi-barrier combination water treatment systems. Professor Wesaal Khan, please give her a round of applause.
Is this one on already? Okay, I just got them on my band over here. Okay, sorry. So that one is on. I must just put the other one on. Okay? Okay. Good evening, everyone, and welcome to my inaugural lecture, which is titled Safe Water is a Human Right, Overcoming the Last Hurdle Towards Water Security for All. So you can see that water obviously plays a major role in what I've been doing for most of my academic career. And I was going a little bit back and forth, and I thought, how am I going to explain why I've spent more than 20 years of my life focusing on water research? Sorry, I just want to get sure the clicker is on. Focusing on water research. And I was going and I was thinking about it, and I thought, you know what? I'm going to lay a foundation. I'm going to start with a problem statement. I'm going to try and tell you why it is we do what we do. And then I'm going to go a little bit into how we do what we do, exactly what it is that we are doing in our laboratory. And I'm sure Gideon is probably wondering, please, Wesaal, don't put up a map of the world with all the percentage of water in it. But Gideon, you knew I was going to do it. Now, if I'm going to start with laying the foundation, surely I've got to tell you what we've got available. And what we've got available, NASA released this beautiful image. I think it's an amazing image. It was taken from space, and it shows you the blue, which is obviously all the water on Earth. And if you do a little bit of a calculation, you'll actually see that about 71% of our Earth is covered in water. But then in my opinion, NASA did something even more amazing. They took all the water on our planet and they compressed it into one single little bubble, and they then worked out in relation to the Earth's biomass, that is approximately how much water we have on the planet. And I kept on reading their literature. I was going back and forth, and I thought to myself, that looks very small. That really can't be true. But okay, it's about half of North America. This, according to NASA, is how much water, if we compress everything in relation to the Earth's biomass, is how much we have on our planet. Now, if you paid attention, you'll actually see that there's another little bubble. The first one, that 71%, that is the seawater. That is the icebergs, that is your glaciers, that's every single thing we've got on this planet, all the water we've got on this planet. Second little bubble, the 2.5%, it's the water that I have available to use, water that you have available to use. It's the water that they have in industry, the water that they have in agriculture, in anything you can think of. That is the water available to all of us. It's in our dams, our streams, our rivers, under the ground as well. And suddenly I'm thinking, I thought that bubble looked small, but I think that bubble is much smaller. We're talking about 2.5% of water that we have available to use. Now, that it caused you a little bit of stress, then that is justified. But a lot of scientists had exactly the same thought, and they decided, we're going to take a lot of data that is available to us. We're going to look at rainfall patterns. We're going to look at precipitation. We're going to look at temperature changes. We're going to see how the population is growing, a lot of factors. And we are going to determine what water we are going to have available by the year 2040. And now you're thinking 2040 is in the future. It's about 17 years away from where we are now. It's not that far in the future. And they saw that many countries on our planet are going to be qualified or classified as what they call high water stress countries. And now you're thinking, okay, that is very bad, especially for the Middle Eastern countries over here, but where does South Africa fall? By the year 2040, South Africa is going to be classified as a high water stress country. What does water stress mean? It means that we use more water than we currently have available. And that is a major concern. And now, the last time any of us thought about water stress, I'm going to say, was about 2016, 2017, when people were driving to game, macro, and stocking up on all their water supplies, when people were buying the rainwater tanks. It's because we were going through a major drought in that period. And that is at the forefront of our minds. We are water stressed. But at the moment, our dams are at 95% capacity. And I just took that off earlier in the week, and I thought, that is a high capacity. We know we're coming off a very high rainfall period. We also know that we still have June, and now we've got July and August. And if you know anything about the Western Cape, those are our high rainfall months. So I'm thinking, okay, the drought is no longer our reality. We're at 95% capacity. Surely the Western Cape is fine. Surely there's no problems in the Western Cape. But what if I told you the following? Before we went into those 3 years of drought, the dams in the Western Cape the very year before was at 86% capacity. And that is quite a high percentage. So anything can change, rainfall patterns can change. We have no idea what's going to be happening next year. What if I told you the following? Earlier the year, the Minister of Water and Sanitation released the following statement. Areas experiencing water shortages are mostly rural areas in the provinces of, and then he mentioned quite a few provinces. So that water stress that we were thinking of is going to happen in 2040. Earlier the year, that was a reality in many of our provinces. I can't remember who it was that said something to me that they were going to go visit family in Beaufort West, and the family actually said to them, don't bring chocolates, don't bring flowers, bring water. This is what they wanted them to bring into Beaufort West because they were experiencing these drought conditions. So now you can understand why most of the world is apprehensive about the high water stress qualification or classification, but why South Africa should also be a little bit apprehensive about that classification. But let's take a look again at where our dams are at, 95%. That's quite a high number, isn't it? And we're still going into, as I said, a higher rainfall period. So then my head was going, okay, so we've got the dams at 95% at the moment, which in my head is quite a high percentage. How much am I using of that supply on a daily basis? So I'm just going to use me as the guinea pig over here and take you through my morning routine. And then, just for argument's sake, let's pretend that this is what I'm going to be doing every morning, and this is how much water I am using. So we've got 8 liters, and it's not those fancy low flush toilets, it's a normal toilet. We've got about 8 liters of water that we're using over there. We've got 6 liters of water when you wash your hands. You've got 5 liters of when you brush your teeth and the tap is running. Now you bring in the shower, it's another 50 liters. And now you're thinking, okay, a couple of cups of coffee, and we're taking that up to 75 liters. That's not a lot, right? 75 liters, it's a little bucket. What is the volume? 50 liters of a bucket, so it's 1.5 little buckets. It's not a lot of water that Wesaal is using every morning. Now, say, for argument's sake, Wesaal repeats that in the evenings. She now runs water for irrigation. She's running her dishwasher. She's running the washing machine. Suddenly, the latest stats or census actually shows that we can be running, on average, in South Africa, about 240 liters of water per person per day. And that's quite a substantial little tank, if you're going to be thinking about it. But now I'm thinking in my head, okay, so Wesaal on average is using 240 liters of water per day. How many of us are using 240 liters of water per day? And again, we go to census or the stats, and it says that in South Africa, 89% of the inhabitants or of the households have access to a water supply. So now your brain goes, okay, so 89% of the population in South Africa has access to 240 liters of water per person per day in their house. And if that is what you are thinking, then you are going to be 1,000% incorrect. Because if you break down that stats just a little bit more, you'll find that the wording said in South Africa, 89% of the population or households have access to a water supply. Nobody said it was in their house. So then we end up with only 45% of our population have access to a piped, coming from the municipality, water supply in their dwellings. If you do the mathematics, it's a very easy little equation. That means that approximately 55% of our population, they do not even have access to tapped or piped water coming from the municipality in their homes. They may have access to a water supply on the outside or on their property, such as a standpipe system or outside tap, but in most cases, they could be using rainwater, and in some cases, they are also using surface water for a lot of their domestic activities. Now, that part of the population, the 55%, they're not using the 240 liters of water per day. They're using 25 liters at a maximum of water per person per day. But I want to say something very quickly. The water that we have the luxury of using every single day, the water that when we open the tap, we brush our teeth, and we don't even think about it, we just go on with our days. That water is coming from the municipality, right? Water that in a standpipe, for example, in an informal settlement, or on an outside tap on a property, that's also, in most cases, coming from a tapped water supply from the municipality. Now, that water is treated. And I'm going to say something maybe a little bit contentious. People may disagree with me. The water in the Western Cape, in my opinion, is of the best water quality in the world, if the water is treated correctly. So we all have access to that wonderful multiple treatment strategy water supply. But now we're looking at more than about 55% of the population. I don't see a treatment system over here, nor do I see a treatment system running next to the surface water supply. So that means these are open water supplies, and these water supplies, various elements, various points of contamination can actually enter these water supplies. Now, if anything can enter this water, which in our lab we call alternative water sources, right? It's environmental water sources, but we use the term quite a lot, alternative water sources, then that means that microorganisms can also enter those water supplies. And that makes the water unsafe. We have water that is going through all these treatment protocols, but a large portion of our communities have water that are actually contaminated with these microorganisms. And that is why we focus on these alternative water sources in our laboratory. We make sure that we go in with monitoring of these water sources. We then know, once we know an idea of what exactly is in that water, we then go in with treatment systems of those water sources as well. A secondary aim, Tando's name was mentioned. I don't know if Tanya Clements is online as well, and Ben focused on it. They look at these secondary metabolites targeting multi-drug resistant escape pathogens, but that is done in collaboration with biochemistry. So today, we are going to be focusing only on the innovation in the water quality, and also or the monitoring as well as the treatment of the water sources. And before I go any further, I'm going to put up this group of young people over here. These are the postgraduates, the masters, the PhDs, some of the honors students as well. Some of them then went on to do postdocs. So it's a collaborative effect. There's actually a team in our laboratory, right? It's not me doing the research, it's this group of people over here doing the research, having major discussions with me once a week where we have to go through all our experimental planning, etc. So the slides you are going to see from this point onwards, it's the experimental research was conducted by most or some of this group of people over here. So let's take it for granted. Let's go through the following scenario very quickly. If I collect a water source, if I go to the environment and I take a water source out of that environment, my job is to understand, is that water safe or is the water unsafe? So what am I going to do? I'm going to go to your local municipality and I'm going to say to them, I want you to test that water and tell me if it's good enough for drinking or if it's not good enough for drinking, whether the water is going to be contaminated. And whoever is in the laboratory at the municipality, one of the first things they are going to do is look for a group of microorganisms called the indicator organisms. Now, as the name implies, it gives me an indication as to whether the water is safe. It gives me an indication as to whether the water may have been contaminated. So this is what the indicator group of organisms does. So I go into the lab at the municipality and I give them the water source and I say, please test this water source for me. And they're going to do the following. They're going to put that water source on what we call culture media. Culture media is a plate where we've got all the nutrients that the microorganisms like. We then put it at the temperature the microorganisms like. We know what pH they like. We know if they want oxygen, if they don't want oxygen. There's a whole lot of factors that come into play. But after a certain time period, we count these indicator organisms. And based on what you find, you can actually determine, yes, that water is good, or no, that water is not good. It's called the South African national standards, but there's international standards. The World Health Organization, the Australian Drinking Water Guidelines, there's a whole lot of them. But based on what you find in that plate, you can say, yes, the water is good enough, or no, the water is not good enough. Or yes, contamination entered my water source, or no, contamination did not enter my water source. And this is, most cases, what they are going to be doing. Here's a problem. That is an analytical laboratory. That is the first thing that they are going to be doing. But if you look at most of the water research groups around the world, there's actually limitations with these indicator group of organisms. Number one, I said we put them on a plate. A plate is where we coax them into growing. We give them everything they need in order to grow. And we take it for granted that these indicator groups, these are just some of their names, they represent all the microorganisms that are out there that could be potentially harmful to various community members. Less than 2% of bacteria can be grown on a plate in our laboratories. We don't know yet what food they need. We don't know what pH they need. We don't know if they want oxygen or they don't want oxygen. So that's the first problem with these indicators. They don't represent all the bacterial population. Second problem, if you are in a water source, I want you to imagine that there's almost no nutrients in that water source. In our world, we call it an oligotrophic environment. So these organisms come from an environment where we've given them almost no food. They go into a preservation state, and then we bring them to our laboratory, and now we want them to grow. But there's a problem with that. These organisms are alive, but they won't grow on our plate. We call them viable, but not culturable. So the indicator organisms are not representing this group of organisms. Now there's another problem. Final problem. This, if I show a second year this, they will say, oh, that is a beautiful streak plate. But what you can actually see over here is growth. Something grew on a plate. This is microbial growth. That, in our world, an empty plate is no growth. So if I bring that water source to the municipality and I say to them, you know what, I need to know if this water source is clean, if the water source is good, and they say there's no growth, I can confirm your water source is safe. But again, they put it on a plate. Now I go in with another method and I find other microorganisms, disease-causing microorganisms in that water source. That means that my indicators or that result was false. It wasn't correct. So what we say is there's a poor relationship between the indicators and disease-causing organisms. We call them pathogens. So there's a lot of problems or limitations with the indicator group. So what do? We take an environmental water source, what we call alternative water sources. We look for disease-causing organisms in that water source. But before we even start the procedure of any method that we want to apply to that water source, we still do the indicators. And you're thinking, I can swear this, that she just gave me all the limitations of the indicators. But the reason we do that is because we want to determine whether we find any of these disease-causing organisms. What did the indicator results say? Was the water safe or was the water unsafe? Was there contamination or was there no contamination? So we always compare all our water sources first to the standards, which are published. Now, you know, when I'm teaching my second years especially, because by now the third years have this knowledge, I always say to them, you are exactly like a microorganism. You get your DNA or your genetic information from your parents. Microorganisms are exactly like you. They get their genetic information, their DNA, from their parents. We call it the mother cell, in fact. So instead of me looking at whether something can grow on a plate, what we actually do is look at the unique DNA fingerprint of the microorganism. And any biology lab, most biology labs, in fact, will perform this procedure. They take out the DNA. In our case, we take out all the DNA from that sample. We run a method that is applied in almost all biology labs around the world called the polymerase chain reaction, meaning you just make more copies of that DNA. Why do we want to make more copies? Because we want to determine what the names are of the microorganisms that are in that samples. So we go in and investigate, looking for certain groups of microorganisms that in most cases you are going to find in a water source. And now everybody's thinking, what about Vibrio cholera? We know that in the north of South Africa, we've got a Vibrio cholera. I'm not going to call it an epidemic, I'm going to call it an endemic, right? It's endemic to that region at the moment. And I did a little research this morning, and the NICD, the National Institute of Communicable Diseases in South Africa, the CDC in the USA, they're going in, putting Vibrio on a plate, but if they don't have anything growing on a plate, they're also looking for her DNA. They want to tell you what strain of Vibrio is causing the outbreak in the northern parts of South Africa. It's actually Vibrio cholera serotype 01L2 in most cases, right? That is causing the outbreak. That's useless information, but yes, this is one of the methods that they are also using to look for Vibrio cholera or identify Vibrio cholera. So what can we tell you? We can tell you if a microorganism is present using PCR. We can tell you if it's absent. We can give her a name. But what we can't tell you is whether she's alive. Now, that's a problem. A microorganism that is alive is producing harmful substances such as toxins that can cause disease. So we want to discover, using various methods, whether these microorganisms are alive. So we go back to the DNA. But what do we do with the DNA at this point? We add something called a viability dye to tag our DNA. Now, as the name implies, viability means life, right? It means alive. So what is the principle of this viability dye? So, you know, I always go back to my second years because I just love explaining things to them. So if I am a microbial cell, this is me, and my skin is my membrane, right? If my membrane is intact, meaning there are no cuts, there are no tears, there are no breaks in my membrane, then I am considered alive. But if my skin has a break in it, meaning my membrane, considering I'm now a microorganism, if it has a tear in it, if there's lysis is what we call it, then that viability dye can enter that cell, attach to its DNA, and the following is going to happen. When we run our methods And in this case, we could use quantitative PCR, for example. The cell that was dead and had the viability dye tagged to each DNA, it is not going to be picked up with our quantitative PCR method. It is not going to be picked up by any method that we are going to be using downstream. That cell, in fact, my sister said to me, oh, so it becomes invisible. Yes. In fact, it becomes invisible because it isn't going to be part of our pool of microorganisms that we are going to be detecting. So we are only going to be picking up the cells with the intact membrane, and we call them alive. So what can we do with the methods to date? We can tell you the names of the microorganisms. We can tell you if they're present. We can tell you their numbers because it's a quantitative PCR method. We can convert those gene copies to cells, simple little equation. And now we can tell you if they are alive. And you must be thinking, okay, that's nice. We've given you a nice picture, but we weren't happy yet. Ben is smiling and Brandon, because they know. We were thinking about it, and you can run a few microorganisms' names, but you are putting in information into the system. I am looking for Legionella. I am looking for E. coli, for example. I am looking for Vibrio cholera. But what about the stuff that are there and I didn't think to look for? So there could be other microorganisms actually present as well. So what do? We take a snapshot of absolutely everything, and we work predominantly with bacteria. We are bacteriologists. We dabble with viruses, but we work with bacteria predominantly. We take a picture of everything that could potentially be in that water sample. So what do? We go back to our viability dye. We first tag the DNA, make sure that the dead cells become invisible. We add it to a method called amplicon-based sequencing. Most of them, it's Illumina, for example. And then we generate an image like this. We can tell you all the families that are in that water source. We can tell you all the genera, meaning every genus that's in that water source. What is a genus? Again, what I say to my second years, my name is Wesaal Khan. My genus is Wesaal. My species is Khan. That is how I explain it to them in most cases. I love my second years. So that is how, in most cases, I would explain it. Your first name is your genus. So the first name of the microorganism we can obtain from this information. And because we use the viability dye, jackpot. We can tell you if they are alive. So, going back to our water sources. And this is surface runoff in an informal settlement. In an informal settlement, you don't have sanitation and drainage infrastructure in most cases. And if you walk into an informal settlement, you know that a lot of times the kids are actually playing in these water sources as well. So that's why we also sample the surface runoff when we go into our informal settlements. And we look and we have found almost every disease-causing organism that you can think of. We found Mycobacterium tuberculosis in our water samples. Mycobacterium tuberculosis causes TB. And we didn't expect to find Mycobacterium tuberculosis in our water sample. So when you go in and you look for specific organisms, there is absolutely nothing wrong with that. But we wanted the whole picture. We wanted to know an overview of everything that could potentially be in that water source. So what do we do after that? We know they're there. I can't go to the community members and say, you know what, I was very excited, I found Mycobacterium tuberculosis in your water sample. It doesn't mean that much. I found Legionella in your water sample, but what we're literally saying is, we found them, please continue to use that. That doesn't make sense. So once we find them, we get an overview or a picture of what is in there. Our next step is to kill them. We've got to kill them. And that is where our treatment systems come into play. Now, there's a lot of treatment systems. My mommy sent me a WhatsApp a couple of weeks ago, and she said, Wesaal, the people in our club are worried. How are we going to treat the water? Can we use jik? I'm like, there are protocols where you can add a little bit of jik to the water, but again, Cape Town, we were okay. You know, there's no cholera in, I'm not going to say that. We don't know if there's cholera in our municipal supplies, but we should be okay, right? So you could use low concentration of sodium hypochlorite. You could use chlorine to treat your water. People use filtration. I know a lot of people, when you were going through the drought, had this fancy filter system set up next to their rainwater tank. A lot of people were doing that as well. Here's what we wanted to do. We want large-scale water treatment. I have to make sure that many community members get a good or a safe water source or safe water supply. So we do large-scale water treatment. This is a solar pasteurizer. It uses very high temperature to treat the water. We've got a holding tank of about 120 liters. Then we've got this system over here. It was part of our EU project, Brandon, 88 and 140. Yes, that was 2 systems we were running. That was the water we were producing after we would run it through our treatment. And that is solar disinfection, UV, and also solar mild heat to treat the water. Whatever we test, I've got to start by saying the following. We start in our laboratory. We don't start anywhere else but testing small-scale systems in our labs, making sure everything is fine. Once we think the system is optimal, we've tested the efficiency, we can say we get rid of almost all the microorganisms, we go to the farm. Stellenbosch has a Welgevallen experimental farm. We've got a little pilot scale system set up on Welgevallen experimental farm. So we test it in the lab, we take it to the farm, and we test it on the farm for about 8 months. Sometimes we're running experiments up to a year, and we simulate whatever conditions we need on our pilot scale or on our farm in the experimental conditions. But now we tested it and we can find, excellent, the system works well on the farm. So what is the next step? We can't keep it on the farm. Nobody can use it there. The next thing we're going to do is take it into the communities and treat the water. And I see Julie smiling because Julie knows. In any community you are ever going to be working with, you need to understand that you are going in and you are occupying space. It's like someone coming into my house, walking in, sitting down and saying, that is my room. And I'm like, I've never seen this person in my life before. You have got to go in and introduce yourself. You've got to explain to the community members you are going to be working with, this is why I am here. This is what I would like to do. And then you go through a maintenance, going through the system, explain, this is your part in making sure that the system works well. This is how you use the system. We want you to only use certain containers to collect the water because we want to make sure that what we're testing is coming just from the system. We're not introducing any of the contaminants. A lot of the time we also work with co-researchers. On Monday we went to the Pebbles Project Trust. It's a daycare for farming community learners aged between 8 and 18. I couldn't say anything to them because they are predominantly Afrikaans speaking. So I was in the background, myself, Jane, and quite a few people, in the background. So if I go into a community and I'm speaking English, I can't take it for granted that everybody understands because you can also see I speak at quite a pace. I speak fast. So now I'm thinking, I'm going to explain this to you and you must all just keep up because I'm going to tell you exactly what I'm doing here. It's not going to work like that. So we work with co-researchers. In most cases, translational service will help us to explain to the community members exactly what we are doing in their communities, why we are occupying this space. We then also have our co-researchers on the information pamphlets that we give our communities. So if anything goes wrong when we are not in that community, our co-researcher will call us and say, pipe is broken, leaking tap, something is happening, you guys need to come out and fix it. So that's important that you always have a contact in the community that you're working in as well. We obviously also apply for ethical clearance. But there's something very important that I need to stress over here. We are still in the testing phase. We tested it in our labs, we tested it on the farm, and now we're testing it in field trials in the communities. So we always ask that the water never be used for drinking purposes. That's ingestion. We say that the water can be used for cleaning, laundry, washing, cooking. How can we say that? Because we've tested it. We've tested it going through the farm, testing the efficiency, going in our labs, testing the efficiency. We know exactly what is in there. So this is not us making it up. This is a recommendation based on our results. And that is why we leave all these pamphlets with all our community members, and we've also got the contact numbers of our co-researchers on those pamphlets as well. And then we put the system in the community. The community gets to use the system. While the community is using the system, we will actually say to them, we are going to come in once a week, once every 2 weeks, and we are going to test the quality of that water while it is in your community as well. And when we're done, we ask for advice. What did you like? What didn't you like? What they really liked, our community members, about this system, it was giving them hot water. It's solar pasteurization. We're talking about temperatures about 75 degrees Celsius. So they were saving money because they were not buying paraffin. So this is a system that they were in favor of as well. So then what do? Well, we use all our other methods I explained to you, but the one that gives us an overview of almost everything is the amplicon-based sequencing linked to the viability dye. So now we can tell you what organisms were present before we put in the system, in the untreated water. Then we can tell you which organisms survived the treatment system and were present after the pasteurization or the solar disinfection. Now, there's not a lot of organisms that can actually survive that, but there are quite a few. And the ones that we found were your Legionellas, your Pseudomonas, and your Klebsiella. There's various ways that they can survive even in that treatment system at 75 degrees Celsius. So what do? You know, I'm not gonna lie, I was memorizing, going through the speech as I was laying in bed, morning, evenings, the whole time. And every time when in my head I got to this slide, the saying came into my head, the enemy of my enemy is my friend. And I thought to myself, that makes so much sense. A bacteriophage is a virus that attacks a bacterium. It is the enemy of a bacterium. A predatory bacteria, which is that one over there, is a bacterium that attacks other bacteria. So these are the enemies of the organisms we want to get rid of. We call them biological agents. Now you can almost guess what we're going to do next. We take these biological agents, the bacteriophages, the predatory bacteria, some people call them vampire bacteria. We combine them with our systems, and we try and treat that water where we get rid of almost all the microorganisms. So we call this a pre-treatment and this a primary treatment over here. And then we go in and we take a look at our results. Did we get rid of almost all these microorganisms if we go in with our combination treatment? And this is results from, I think it was Monique's PhD, where we tested the predatory bacteria with a solar disinfection method. And here you can see the counts are actually at 0 for the microbial cells. They went to below detection limit is what we call them. So that was first prize. We were very happy about that. We went in, we took them out with their enemy, and then we went out and we took out the enemy and the remaining microorganisms. Because that's what my sister actually asked me. She says, but Wesaal, with COVID, aren't people scared that you're bringing a virus into a water source? Well, that's what the secondary or the primary treatment does, the solar disinfection. We get rid of the virus. We get rid of the predatory bacteria as well. But if you'll see something over here, there are some microorganisms. We reduce their numbers. The system works efficiently, but some of them were still surviving. So now our next step is to know, if you are still surviving at the number that we find you at, is it safe for the community to use that water? Because we got rid of almost all the other microorganisms. And this is where risk assessment comes into play, which is the final thing that we're trying to do with our research as well. Using a risk assessment model, we can take a look and tell our community members, based on the levels of the microorganisms we are detecting in your water source, you can use that water for garden hosing, for laundry, for washing, bathing, and cleaning the home. You should not use that water for playing, for garden work, and for accidental consumption. And this is where risk assessment plays a crucial role. It calculates the risk of using a water source even after we've come in with our treatment strategy as well. So we get our environmental water sources. Our lab calls it alternative water sources. We look for all these microorganisms using all the methods I just went through in these environmental water sources. And then we use biological agents as well as our solar disinfection methods to kill as many of the microorganisms as we possibly can. I'm going to say the biological treatment, we are still at the lab stage. We're hoping to go into the field work or the pilot scale stage at least in the next year with that system as well. Now, why do we do all of this? We know that 55% of our population, they don't have access to a tap water source in their dwelling. But this is the Sustainable Development Goals. We want to make sure that we are not only giving people a water source, we are giving people in our country a water source to use, but we're giving them a safe water source. So with these goals, these are the two primary ones that we aim to achieve with our research. This is my dedication. All the people that have ever been in our laboratory as well, our collaborators, as well as our funding institutions. And then, you know what your biggest fear is when you do something like this? You forget a name. So you say all your family, all your friends, and all your colleagues. So that's where you're not going to forget absolutely anybody. Thank you very much. This one? Oh, sorry. Oh, you know. Yeah. Thank you.
Okay, good evening, everyone. You look sad. After such an amazing talk, I think we should give her a big clap again. Thank you so much. I'm sure it's not that the people are afraid. It was very inspiring, and I really want to thank you, Professor Wesaal, for the talk and for being able to explain it to the public. I think I've never understood water the way you explained it. So it's true what our dean said, that she's a great teacher and mentor. So yeah, we want to thank you just for that. So thanks so much as well for really delivering a successful talk this evening. So we know that, of course, the title of the talk today was Safe Water is a Human Right, Overcoming the Last Hurdle Towards Water Security for All. And we all know, I found a quote which I thought was very interesting, and so as you were speaking, and it talks about, you know, that it says that thousands have lived without love, right? But no one has lived without water. So which I thought is really profound. So it talks about the importance of water and what it means to us. And I think I really liked also the, you know, the visuals that you showed, especially around the NASA image you had, which shows the percentage of water which is there, and then the amount that is available for use, which is really a small percentage, 2.5%. That's very scary. And of course, I think the last slide, which really talks to some of the global issues that we try to address, which is aligned to our, you know, research strategy as a university, Sustainable Goal 3, which talks about, you know, trying to achieve good health and well-being for all the people in the communities. I think you also touched on access to water. I think access, so we have access, but access is not really for everybody. So which is still the status, which is a big concern. And then also you did talk about, you know, the work which you are doing, which is really trying to make sure that we find, I think on the innovation side, really trying to have practical solutions which can help to tackle those problems. It's one of the best examples I've seen of how you translate research into practical solutions. So starting from the problem itself, the skills training for students, but I guess also working with the city, you know, the community engagement, which is really profound. And I think I like one of the key points you mentioned around, you know, trying to, when we go into these communities, the fact that we have to also bring them to the party, and some of them being playing key roles as part of the research participants, and I think that contributes to skills training. So at Stellenbosch University, as you know, we are a research-intensive university, and we really drive research and innovation. And recently, we've been approved as one of the universities that should lead the African Union, European Union agenda, where we are hosting 4 clusters. And of these clusters, we have one cluster which is on renewable energy. And I saw that, in this talk as well, there's the fact that water is critical. And water also addresses issues around renewable energy and how we can use that also to translate sources. So I see a big nexus between water, health, climate change as well, and how that can form interdisciplinary collaborations, to solve and tackle some of these problems that we face as a country. Of course, we do encourage our researchers to take up opportunities, of course, to apply for grants, but you also saw that around the partnerships as well, the range of collaborations and partnerships. I think it's this slide, yeah, that's my favorite slide. And I probably wanted to boast that it's because we spent time at CUT, that's why you're able to do the translation so well. But but it's really good to see the partnerships that are there. And these help us, of course, to make sure that we can access additional funding. We know that as a country, our funding into research has reduced over the years, but this gives us a great platform as well. So the African Union agenda, of course, focuses on a number of areas which involve, there's the health area, which is green health. There's also the area that talks about innovation and technology. So we do see this area as one of the areas which can really also help us to access those funding in order to do the work that you do and to support. Of course, the Water Research Council is a key player, so I'm glad to see them that they're also contributing. And you may ask, why do we do this? Why do we have lectures? It's a cold night, and we're here, and we're listening to this water lecture. But as a university, the inaugural lecture really is an auspicious occasion for the university and to the candidate themselves, as it shows the amount of work they've done that has brought them to this stage to become full professor. So I want to use this opportunity as well, and the fact that, do we have any community members present tonight? Anyone from the community who's not an academic in the audience? I saw Professor Tulio, you're an academic. Anyone else who's not an academic? Family members, raise your hands, yeah? So you can see, did you understand the lecture today? Yes. You can explain to our grandparents what you did tonight, yeah? So I think it's really important for that. So for us, it's also important to be able to interact with the community during this time. So I want to use this occasion to congratulate you again on the full professorship. And congratulations, please give her a clap again. Thank you so much. Okay, thank you so much.
Good evening, ladies and gentlemen. A word from the department. First, now we can see why Wesaal has got rock star status among the second years. Wesaal, we are very proud of you. And we are privileged to have you in our team. Thank you. That's all I want to say. Okay. I also want to thank a lot of people that made this occasion worthwhile. First, the most important ones, Wesaal's family, especially her mother, Cecilia Muller. Thank you for your attendance here. Also, her brother, Walid, yes, I forgot. Walid, thank you for being here. Thank you for being here, and we are happy that you are here. And yes, her sister, Siam, thank you that you came here. And thank you, I know your sister is very proud of you. as deputy, how can I say, DVC. That's it. It's a long title, but thank you. Yeah, thank you that you came all the way from Joburg. Also, I want to thank all the other family members that came here today, and Wesaal's friends, their colleagues from CPUT and Stellenbosch that attended this meeting online as well as face-to-face. Yeah, thank you very much for coming. Then I also want to thank a whole list of people who basically made this occasion worthwhile. First of all, yes, from the Registrar's Office, Jonathan Dale, where are you? You're sitting there at the back. Thank you very much for all the basically all the organization of this. Okay, I saw this morning still a reminder from your office. Thank you. Then also from the rest of the marketing team. I don't know where they are, where they sit here, but Amira Brown, thank you for your input here. Olivia Adams, she was here somewhere. Thank you. It was very nice organized here. And Giola Abrams and Cindy Arendse, I'm not sure if they are here, but thank you for all the trouble you had here. And also the communications team. There at the back is Justin Alberts and Ilse Grobler. I'm not sure if she's here. I didn't see her here. And Renee Jean van der Berg. They were the guys that actually set up all the computers and so here, and they make sure of the communications. Then from the faculty, Suzette, yeah, I'm not going to ask you to stand up. Thank you for your organization, and Johan van Zyl as well. And of course, finally, Professor Moyo, Professor Warnig, Revitsky, and Scholes. Thank you so much for all your support and leadership you showed us, the department, in the past few years. We really appreciate that. Thank you. And now I've got the important, how can I say, job of asking you guys or inviting you all to come and join us in the foyer for some refreshments and cocktails. Thank you very much.
Please stand as the procession will leave the venue now.